Okay, so let's talk about 3D holograms. You know, the kind you see in sci-fi movies.
Right. Interacting with light, seeing objects floating in the air.
Exactly. That kind of stuff. It always feels like it's just around the corner, but, well, maybe not quite.
And getting really good high-fidelity 3D images.
Mm-hmm.
Uh, Especially with certain types of light or in tricky situations, that can be tough.
Yeah, technically really challenging or just incredibly expensive.
Traditional methods, they often hit limits. You need specific setups, controlled environments, sometimes very specialized detectors for, say, infrared light.
And getting that depth information accurately at the same time adds another layer of complexity.
It really does.
Which is why the source material we're looking at really jumped out. It's about a breakthrough reported from Brown University.
Mm.
And get this, apparently spearheaded by 2 undergraduates, which is pretty amazing in itself.
It is. And what they've done is find a way around some of those hurdles by using, well, quantum physics.
So they haven't just tweaked things a bit.
No, it seems much more fundamental. They've actually woven quantum entanglement into the process of making 3D holograms.
Quantum entanglement. Okay, that's the spooky action at a distance thing Einstein talked about.
That's the one, where two particles are linked, intrinsically linked, no matter how far apart they are.
And they're using that link to build an image, a 3D image.
That's the core idea. It's a fascinating bridge, really, between quantum mechanics, which can feel pretty abstract, and the very practical field of imaging.
Wow.
And as the source material lays out, this approach has some potentially huge advantages, like cost, for one,
Right.
and being able to image in wavelengths like infrared, but without needing those super expensive traditional IR cameras. Plus, capturing precise depth.
Okay, so that's our mission for this deep dive then. We want to unpack this for you, our listener.
Hmm.
Figure out how this quantum multi-wavelength holography, as they call it, actually works. Why is using entanglement such a big deal here?
And what could it mean down the road?
Yeah, for things like medical imaging, manufacturing, maybe even those futuristic displays we were just talking about. Let's get into the spooky side of light.
Let's do it.
So the absolute core of this, like you said, is quantum entanglement, these linked particles. Measuring one tells you about the other instantly, wherever it is. How on earth do you use that to see something?
Well, it starts with making the entangled pairs. The source explains they use a laser beam,
Okay.
and they fire it at a special kind of crystal, a nonlinear crystal. You can sort of think of it like a light splitter, but, a quantum version.
Quantum splitter, right.
So when a photon from the laser hits this crystal, sometimes it splits into two new photons,
Yeah.
lower energy ones.
And these two are the entangled pair.
Exactly. And in this specific setup, they generate one photon in the infrared spectrum, the idler photon they call it, and its partner, the signal photon, is visible light.
Okay, got it. So pairs born together, linked forever, one infrared, one visible. What happens next? Where do they go?
So this is where the really clever part comes in, according to the research. The infrared photon. That one gets sent towards the object they actually want to image.
Ah,
It interacts with the object's surface, bounces off, scatters around, and as it does that, it picks up information shape, texture, and importantly, its depth. How far away different parts are.
so the infrared one is the scout. It's the one actually seeing or, well, touching the object.
Precisely. And here's the entanglement magic, its partner. The visible signal photon. It goes on a completely different path.
Okay.
It never interacts with the object at all, never gets near it.
Wait, really?
Really. But because it's entangled with the infrared photon that did interact, the link between them means the information picked up by the infrared one is mirrored or correlated in the state of the visible one.
Hold on. So the visible photon carries information about an object it never touched just because its quantum twin did touch it.
That's the essence of it, yes.
And then you just detect the visible one.
Exactly. You use a standard camera, one sensitive to visible light. These are, much more common, much less expensive than specialized infrared cameras.
Much less, yeah.
You capture these visible signal photons. Then, by carefully analyzing the patterns, the correlations in how these visible photons arrive, you can reconstruct a detailed image,
Including depth.
including depth, an image of the object that was only ever actually hit by infrared light.
So you're basically doing infrared imaging, but without needing an infrared camera. That feels like a massive practical advantage.
Oh, absolutely. Infrared is so useful, seeing through smoke, detecting heat, analyzing certain materials, but IR detectors are often prohibitively expensive.
Right.
This technique potentially just sidesteps that whole cost issue by shifting the detection part over to the visible spectrum. using that quantum link as the bridge.
Okay, that's clever. But the source mentioned is not just a flat image. You get the 3D, the depth information too.
Yeah.
How does the depth info get into the visible photon that stayed away?
It's related to the phase of the light waves. When light reflects off surfaces at different distances, its phase changes.
Okay.
This phase information, which encodes the depth, gets imprinted onto the infrared photon when it interacts with the object.
Right.
And because of entanglement, that change in the infrared photon state is correlated, it's linked to the state of the visible photon.
Ah, I see.
So even though it's complex, you can maybe think of it like timing or path length. The interaction changes the infrared photon's effective path, and that subtly influences the correlation you observe when you detect the visible partner.
Okay.
By measuring these subtle correlated effects across lots and lots of photon pairs, you can actually build up a 3D map of the object's surface.
And the source said they got pretty good accuracy.
Yeah, the report mentioned achieving sub-millimeter depth accuracy in their experiment.
Sub-millimeter from light that never even went near the object. That's genuinely wild. And they showed this worked by imaging. What was it, a tiny letter B?
Yes, a little metallic B, about 1.5 millimeters wide. It was their proof of concept.
Showed it wasn't just theory.
Exactly. Demonstrated the high-resolution 3D reconstruction and confirmed the depth mapping worked. And they also noted another useful aspect, being able to do this imaging even with ambient light around, which can be a problem for other sensitive holography techniques.
Okay, so let's recap the setup. Laser hits a special crystal, makes entangled pairs, one infrared, one visible.
Right.
Infrared 1 probes the object, picks up 3D info. Visible 1 goes straight to a regular cheap camera. And by analyzing the spooky quantum connection between the visible photons you do see, you reconstruct the 3D infrared view, depth included, without ever needing an IR camera.
That's the core process, yeah.
It sounds amazing. Revolutionary almost. But quantum experiments, especially early stage ones like this, seems to be, they always have catches, right? Practical hurdles.
Oh, absolutely.
Yeah.
This isn't magic, even if it feels a bit like it. While the detection is simpler, getting the whole thing set up initially, aligning the optics, making sure the entangled pairs are generated correctly and sent the right way, that's still delicate work.
Needs precision.
Definitely. It's not something you just, plug in and it works perfectly right out of the box yet.
And I think I saw something in the source about photon yield. Does that mean how many pairs you actually get?
Yeah, exactly.
Yeah.
Generating these entangled pairs efficiently, that's still a big challenge across quantum optics. The process in that crystal, it's not super efficient. You put in a lot of laser light, but you only get a relatively small number of useful entangled pairs out.
And what does that low yield mean in practice?
It means collecting enough photons to build up a clear image can take time, sometimes quite a bit of time.
So not real-time video just yet.
No, that's a significant hurdle right now for doing things like real-time imaging or capturing fast events. Improving that photon yield, making the process more efficient, is a key focus for their future work, according to the source.
Okay, so speed is an issue. Makes sense.
And scalability, too. Taking the whole setup from a lab bench and making it smaller, more robust, more practical for use in, say, a hospital or a factory, that's another step.
But these sound more like engineering challenges, right?
Right.
Optimizing the hardware, refining the process. Not like the fundamental physics is wrong.
That seems to be the case, yes. The core principle has been demonstrated. Now it's about iterating, improving the technology to make it faster, more compact, more user-friendly.
Which, if they can do that, opens up some really, really interesting applications. The source listed quite a few possibilities. Medical imaging jumped out at me.
It's a big one. Using infrared light non-invasively is already valuable. IR interacts with tissues differently than visible light. It can offer unique diagnostic information.
Like for eyes or skin.
Potentially, yes. Ophthalmology, dermatology. Being able to get high-res 3D views using this method without harmful radiation like X-rays, and crucially, without those expensive specialized IR cameras, could make advanced diagnostics much more widely available.
Yeah, I can see that. And what about security? Imaging through fog or smoke?
Right. Things that block visible light are often transparent or semi-transparent in the infrared spectrum.
You could see through them.
If you can do affordable, effective IR imaging using this quantum technique, yeah, you gain a powerful tool for seeing things hidden from normal view. Security, maybe industrial inspection, search and rescue even.
And manufacturing, too, for quality control. Checking surfaces.
Absolutely. If you need really precise 3D measurements, sub-millimeter accuracy to spot tiny flaws, check wear patterns, ensure dimensions are correct.
This could make it cheaper and easier.
Potentially, yes. Faster, more versatile, especially for materials best inspected with infrared.
And then there's the ultimate sci-fi dream, those futuristic displays we started with.
Well, the source does suggest that while full-scale, real-time holographic displays are still a ways off, largely because of those speed issues we mentioned.
Right.
This research lays some important groundwork. It's about capturing the kind of complex, detailed 3D light information you'd need for truly immersive holograms or maybe next-gen AR and VR.
It really feels like this work, sparked by these two undergraduates, could be planting a seed for something pretty big, new ways to see the world.
Mm-hmm. The team is clearly thinking ahead, scaling up, improving efficiency. The source mentions maybe even using quantum computing to speed up the image reconstruction process.
And trying different types of entangled photons, different wavelengths.
Yeah, they suggest exploring other entangled pairs could unlock totally different sensing capabilities, even beyond just infrared imaging.
So wrapping up this deep dive then, we've seen how using this spooky quantum link, this entanglement, lets you generate high-res 3D images, gets you precise depth, and maybe the biggest practical win right now lets you do infrared imaging using cheap, standard, visible light cameras.
It's a really neat example of applying quantum principles to solve classical problems, potentially making complex imaging much more accessible and affordable.
Opens doors in medicine, security, manufacturing. Maybe those future displays someday.
Definitely.
Now, obviously, there are still challenges. Engineering hurdles, like boosting that photon yield for speed, making the system smaller, more robust.
The path forward involves refining the tech.
But the underlying potential seems undeniable. It really makes you think differently.
It certainly does.
Which kind of leaves us, and you, our listener, with this final thought to ponder. We've just discussed how entangled particles have this instant connection no matter the distance.
Right, the non-local correlation.
And this research uses that connection to image something without one of the linked particles ever actually interacting with the object. It gets the information via its partner. So the question is, what else could we measure or detect? What other seemingly impossible sensing could be unlocked in the future just by observing the correlations between quantum partners without needing direct interaction in the way we normally think about it?
It does suggest that the ways we can gather information about the world might be broader, maybe stranger, than we've traditionally assumed.
Exactly. The quantum realm keeps finding ways to surprise us.
Indeed it does.
Well, thanks for digging into this with us today.
My pleasure. Always fascinating stuff.